Welcome. Go ahead and get started. It's 9:01. So I'm John Phillips. I'm a senior product manager in Amazon EC2 with a dedication to GPU instances. It's been exciting to see the interest in GPUs grow over time, and that's one reason why we decided to create a separate session today at reInvent specifically on GPU instances. And now we knew that we could fill the entire 60 minutes talking about features and functionality of our GPU offering, the breadth of API and operating system support, the ecosystem we're building around them, and also how to start using them and get going. But instead, we decided to get a few customers on stage to share their real experiences with us and using our GPU instances. And so I'm honored here today to have Ting from Schrodinger and Yuri from Autodesk, who will talk about their use of EC2 GPU instances, why they're beneficial to them, and actually a high-level view of their architectures. And so what I'll do is just give a brief overview of our history with GPU instances, and then I'll pass the microphone over to them. So EC2 offers a broad selection of instance types to satisfy a diversity of use cases and workload demands. And we've been iterating quickly on behalf of our customers. Now, when you think about the word instance, if you actually look it up in the dictionary, it says a single occurrence of something. So it really invites us to think about instances as having a specific purpose. And that's generally how we've categorized our instances into families. You've got compute-optimized instances, you've got memory-optimized instances, you've got IOPS-optimized instances, and we have GPU instances. And each of these categories align with specific use cases. And so you can see from this chart that we've been offering GPU instances for over 2.5 years now. And we've learned a lot, both in how to pack data centers full of these things and operate and maintain them, and also in terms of customer feedback. So I want to take a second to bring us back to October 2010 when we launched GPU instances and ask the question, why did we get into this to begin with? In a word, performance, and specifically parallel performance. GPUs are designed for parallel processing by offering massive amounts of computational units. And applications that benefit from the use of GPUs include those that demand thousands, tens of thousands, hundreds of thousands, or millions of execution threads. And examples include such things as 3D graphics, where pixels can be operated on independently, or, for example, stock price simulations, where you might consider asset price as independent random variables, and their forward movements can be predicted or simulated in parallel. So we got into the GPU family over 2.5 years ago to provide EC2 customers access to these capabilities. And this was with the CG14 Extra Large, as a beefy instance type with 2 Tesla M2050 GPUs, designed really for the GPU compute market, as they chiefly supported the CUDA and OpenCL programming models. And so this instance type was really intended for applications that would use GPUs as coprocessors or accelerators. And some application spaces that can be accelerated with GPUs include computational fluid dynamics and finite element analysis, stochastic simulations in finance, engineering, and energy, life sciences, including genomics, 3D rendering for computer-aided design, and weather modeling and forecasting. And as soon as we launched this instance type, we started getting immediate feedback. And I'll tell you a few points of feedback. Chiefly that price was too high at $2.10 per hour. The complexity was high, as programming against 2 GPUs was more cumbersome than one. And so there was generally a demand for a single GPU size. And also there was demand for graphics APIs. And interestingly enough, some of our customers were able to get low versions of OpenGL to work on the CG1. And so we had some clear demonstrated demand for graphics APIs, and we knew the family had to evolve. So nearly 2 weeks ago, we launched the G2 2 Extra Large, which we believe accommodates all of these customer feedback points. It offers later generation NVIDIA technology. It offers a single GPU instance size, support for graphics APIs, and actually it offers support for frame capture and encoding technology, which enables a new realm of use cases in 3D application streaming. And finally, it comes at a significantly reduced price of 65 cents per hour Linux on demand in our largest region, US East. And that's 40% lower on a per GPU basis compared to the CG1 extra large. And on an absolute basis, it's over 3 times less expensive. And so I wanted to touch upon this area of 3D application streaming before handing the microphone over, because it is our newest use case, and a lot of customers are considering entering this space. So I wanted to give a few strategy points or themes related to the idea of 3D application streaming that you can think about as Ting and Yuri present. The first thing that customers tend to think about is accessibility. By hosting your 3D applications in EC2 and streaming them, a video and audio stream, to a number of client devices, you can create an instant-on experience to a multitude of lower capability client devices and vastly increase the accessibility of a high-performance 3D application. In terms of quality of service, you're able to do things like manage the quality of the stream and measure the quality of the stream. You can also measure the areas of your application which see activity and those which don't, and report metrics from your application hosted in EC2 into some of our database services like DynamoDB, SimpleDB, or EMR for analytics. And you can use that feedback to iterate on a high-performance 3D application in ways that weren't possible before, creating business agility. So in other words, by hosting applications in EC2, this category can now benefit from the measurement that you might find in web applications and iteration that you might find in web applications in a space that typically hasn't had that level of agility. In terms of collaboration, I'd ask the question of what can you do now when your 3D visualization nodes or application streaming nodes are located within close network proximity with low latency and high throughput. It means that data transfers are no longer expensive in terms of time or cost. So what kind of collaboration experience does this enable for your users of your 3D applications? Data security. The data and application bits never leave EC2, just the video and audio streams. So this enables some benefits in terms of data security if you want to protect your IP. And finally, which I think is the most interesting point in question, is what can you do with AWS under your desk? If you're streaming your 3D application from AWS, that application can benefit from the vast compute and storage resources and other services in AWS, which can enable your application to do things that were never possible even with the most expensive workstation under your desk. And with that, I'll introduce Yuri from Autodesk, who will talk about how desktop apps are the new web apps.
Thank you very much. And so I would like to talk about how the new AWS GPU instances enable desktop app companies to seamlessly move their applications into the cloud and change their software delivery mechanisms from physical media to streaming-based. And so, with that, I will show how computing, hardware and software came full circle from desktop to desktop, from the physical desktop to the virtual desktop into the cloud, and how this will be very beneficial for our customers when integrating their applications and our applications to our cloud offerings. So to introduce the company I work for, Autodesk started in 1982 with only 16 people and a single software title. Today it's a leader in design, software, building, manufacturing, and infrastructure software. Our customers create designs such as the Estadio Nacional de Brasilia. And this, as you can see, this model is rather complex, and it's more than just a 3D model. It's a whole giant data set with complete description of the how the building will work and what kind of ways to construct it, and maybe even how to demolish it in the end. Another example is that our customers doing with our software is digital prototyping. This enables them to test their designs before building it, and therefore reducing the product life cycle by a lot. Finally, another example is the media and entertainment space. I don't know if you know that Autodesk software was used for the films that received the past 18 Academy Awards. So it's been pretty well used. And now, a few words about the CAD evolution. The proliferation of CAD was enabled by this revolutionary new machine in 1982, the IBM PC-286. So this came at a price point that made it affordable to design firms, and that let the CAD software be available for pretty much everybody who wanted it. And so that CAD software started out as lines, drafting, circles, arcs, and evolved into blocks, shapes, and from there, intelligent objects that can be customized, parametric. And the evolution continues today. And with that, the data sets have grown as well. So huge data sets like to live on huge machines, servers. And these data sets contain, as I mentioned earlier, information about the building, not only the 3D information, but whole building information models. That lets facilities monitor after the building is constructed, keep track of parts, replace them, fix them, easily find them. Obviously, it helps with the construction. It helps simulating the construction. And at the end of the life cycle, it helps with the demolition. Simulation analysis is also used in the design process. So as you can imagine, that generates huge data sets, but furthermore, the AWS cloud is used here to simulate the buildings in the design phase. So that means you don't only use simulation for validation at the end of the design phase, but also use it to actually create your building. Here's another example of a humongous data set. This is one of our applications called InfraWorks, and this models whole infrastructures in a city and is able to show, for example, how the change in sunlight affects the infrastructure, how the electricity will be used, and so on and so forth. So from this, it's pretty obvious by now that design is visualization. Therefore, you need pretty good desktop machines, the highest end possible, with good GPUs, good CPUs. And design is also collaboration. It started out as single draftsmen creating their designs at separate workstations and then maybe merging them at the construction site, or maybe a little earlier. But that evolved into whole teams of designers, customers, fabricators working together to create a design, to construct it, and to deliver it. So the relationship between all these people is what we call the design graph. And as you can see, it's pretty complex, and it leads to the data being moved around quite a lot. Now, this leads to versioning, chaos. This can result in huge data sets being sent around, email, FTP servers, FTP passwords, all sorts of trouble. I don't know, you probably had this with your own data sets. And so these are the strategies that can be used to move all that to the cloud. So if you want to move your applications to the cloud, that would provide a solution to this data set problem and the collaboration problem. You can do either move to the cloud by creating brand new applications, brand new services from scratch. Or you can reuse your existing IP and maybe move your applications to server side, removing the UI. Or you can use the whole desktop app now and deploy it on the cloud and remote into it. So Autodesk created a cloud solution called Autodesk 360 that helps our customers in this collaboration and provides them with the history of designs, provides them with a central location for the design files. And now I will try to show you how that can be leveraged, a cloud storage location, a cloud identity service, and other services by using desktop apps that are running by this data, near this data. This is one more reflection on the advantages of using the Autodesk or the AWS cloud for the Autodesk 360 solution. You can access your data anywhere, in the field, in the ditches, underground, on mobile devices, any of the offices you're going to. You can use any device and do seamless collaboration on the data, because the data is sitting in one location. And you can do editing from anywhere. And this is not very obvious, but the fact that the data is close to the application means that the access to the data is much faster. And that can make a big difference. And so here comes application remoting that provides a solution to accessing your desktop applications that you get used to and love in the cloud. So if anybody ever used remote desktop, this is pretty much the same concept, except a little bit enhanced. So you have your application player on the client side that sends over the keyboard and the mouse events, and you get back the video stream from the EC2 instance. And in our use case, you get individual application streams back. These are the technology partners that we're using currently. So your operating system is Mac OS or Windows. Your transport is Citrix or Autodesk. And AWS is also entering this space, so maybe we can see them showing up on this pretty soon. And the Autodesk software is running on EC2 instances. In the future, this might even become smaller as far as the client side is involved. It's already very small, but it's operating system specific. So you have to rewrite your player on all OSs. In the very near future, this can become the browsers. And so I'm going to try to show a demo at the end where we can see where it's headed. A few words about the overall architecture of our application remoting solution. So the stack is deployed in multiple data centers for higher reliability. And the client determines which one is the closest. That data center is chosen, and the client connects to that through a controller instance. And the app servers are running on EC2 instances on demand, scaled up by our own scaling algorithm, which is because of two things. One is the startup time of Windows instances is 12 to 15 minutes. So auto-scaling can be a little bit problematic there. And scaling down is also controlled by us to provide a buffer time. And that way we can reuse the instances if new customers are coming in bursts. And all this is backed by S3 for the application settings and the user data. And we use SimpleDB for the user and session data. To further save costs, we are sharing the instances between our users. So 2 to 4 users can currently share a M1X large instance. And that will probably even further improve in the future. And on the GPU instances, it's going to be a similar ratio. So here's another slide where I would like to talk a few words about how this streaming is. Why is it better than sending around the actual data? You would think that streaming requires high bandwidth and it's going to be more expensive than moving the actual data around, but that is a questionable proposition, especially knowing the size of the data sets. So every time you send a data set around, that will be the size of the data set times the number of times you send it. If you keep your data in the AWS cloud, you only send references to the data, and those tend to be relatively small, and then you have a fixed cost with the bandwidth that's required for application streaming. And even that bandwidth is not always used because users are not always manipulating their data. So there is a maximum well-known bandwidth that's needed, and the reality tends to be lower. And so that integrates with the Autodesk A360 solution, which is already in place. The identity and storage services are running on EC2 and RDS, and storage services are using S3 and DynamoDB. And we also have analytics and simulation backed by AWS as well. And our operations team is also heavily using the S3, EC2, and database services. So where this gets integrated is how it fits all together. You use your application player to log in through the identity service and access your data on the storage. I'm sorry. First, you used to use your desktop apps to connect to the identity service, and then you could access your storage. That was step one. That's how the A360 cloud started. And now, with the introduction of the remote streaming, that was the next step. A few of the applications could be remoted. But at that time, a couple of years ago when it all started, there were no GPU instances yet. But the benefits were already obvious. All the storage was nearby, so to access that was pretty fast. Especially, we have a little piece that's enabling the EBS volumes to act as a cache between the storage services and the actual application. So that speeds things up a lot. So you don't have to download all your files locally. It's just sitting up there, and you're accessing it up there on the EC2 instances. And this is where we're at now. With the introduction of the GPU instances, you can get all the applications. So from just a few, you can move all of them to the players. So from this, you get this. And so, at the same time, if you've been following the evolution of web browsers, they're getting more and more features. They started out as simple HTML rendering engines. And today's web browsers have WebGL, they have CSS3. They're turning into little virtual machines. And I guess that means it can become the new player, which makes player development that much easier. So one final look at this architecture. You have your very thin player piece on the client, any client that has a browser. You have the apps running up in the AWS cloud, close to the data, accessible from anywhere, and backed by the other services. So you have storage, identity, analytics, simulation, so you can do all your simulations during design time, create your design from the results of the simulations, and then you have this other supporting infrastructure. So the GPU instances enable all our applications to move to this model if necessary. Obviously, this doesn't mean the complete abolishment of the desktop apps, but if you want to use your desktop app from a remote location instead of trying to learn some brand new web app that was developed, then there you have it. And with that, I will try to show a demo of our new Autodesk AWS instances, which is a preview that's running our applications. Thank you. So let's imagine that I get a link via email, or I already know this. I turn this on in Firefox, and it connects to the instance. As you can see, it's a preview. And this is running 3ds Max here. They also have Inventor running. So you can, as you can see, it's pretty speedy. And this is a JavaScript client. So, and of course, it's running from San Francisco, or Oregon even. This is, again, 3ds Max. And you can see the remoting speed is pretty good. And you can do your favorite operations, look at it again, maybe do some color changes, change some materials, you know. Let's see, how about this? And so on and so forth. I'm not going to change it now, I like red. So. And same thing with the Inventor. Or you get another, let's say you get another email. You open this link in your browser. There you go. And then you load this other model. And you can look at it, pan around, and zoom in. Just like edit it the way you've been editing your apps, your models on the desktop. And with that, thank you very much. And I will hand the microphone to Dan.
GPU is capable of running on many different kind of applications. In addition to the application you just see a couple of minutes ago, the new generation of the GPU could use to do scientific computing as well. Today, I'm going to share with you how we utilize the GPU instance on AWS to do drug discovery. For those of you who are not familiar with drug discovery, it has very many different stages, ranging from the pre-discovery, drug discovery, preclinical, and 3 different stages of the clinical trial. The whole process is very complicated, and it takes up to 15 years, and it costs around $1 billion. Since the core competitive advantage of the pharmaceutical company is in R&D, so 15% of their revenue is invested back onto the R&D, and a significant portion of those is onto the go onto the drug discovery. A few simple facts about the drug discovery: each drug candidate has a value of $100 million, but it costs pharmaceutical company, in average, $50 million to produce one. And the successful rate is only 1 out of 3. economic cost is only part of the equation. The most important thing for them is really the time to go to the market and the opportunity cost. So pharmaceutical companies are looking for innovative technology to bring the drug to the market quicker with lower cost. Computer-aided drug design it's among one of those innovative technology. And Schrodinger, we have several products to help the scientists to design the drug molecule. And we also have a visualization platform, PyMo, which is an open source product to allow the people to visualize the 3D structure of the protein and the drug molecule as well. Ligand protein binding is one of the most important phenomena in drug discovery. In biochemistry and pharmacology, ligand usually is referred to the small molecules. So let me play a quick video to show how the ligand will bind to the protein. So the white surface you hear, what you see here, it's the protein. So as you see, then moving molecule is the ligand. It tries to find its way into the binding pocket. And when it finds the binding pocket, it stays there and changes the conformation of the protein. Consequently, it will change the biological function. The tendency or the strength of the binding, it's called binding affinity. It's very critical in the drug discovery. And how to predict this binding affinity very accurately, it's considered as the holy grail of the computer-aided drug design. Free energy perturbation, or FEP, is one of the most rigorous ways to compute the binding affinity. I'm really excited to announce after 7 years of R&D, as yesterday, we have an official release of FEP product, allow us to predict the binding affinity very accurately. In order to make this FEP product practical, it has to be accurate, and it has to be easy to use, and also run fast enough. The accuracy of the FEP depends on the sampling algorithm and the force field parameter. So we have been making a lot of progress on those two areas. And previously, for a FEP expert to set up one calculation, it takes up to a few hours, several hours, and up to a day. So we now could generate the perturbation network for tens of molecules just in a couple minutes. And the introduction of this perturbation network also brings this FEP calculation to the next level. Instead of looking at individual calculation, we are now looking at the whole network, which will also improve the accuracy. And FEP calculation is known to be very slow. It takes 3 or more days on 96 GPUs, and it's not very reliable because the cross-node calculation. On the other hand, running on GPU, it's a lot faster. And what you see here on the last column, it's the performance on the new G2 instance. So it's about almost 50 times faster than the single CPU core. So how can FEP help the drug discovery? Traditionally, every single project so chemists have to synthesize thousands of compounds for every single project. And each compound will take weeks or even months to synthesize, depending on the chemistry. And each one of the compounds costs $1,000 to $5,000. And if you're using the FEP technology, you could finish one calculation in 6 hours. And it costs only $75 on CG1 instance, and the price going down pretty quickly. I have a conversation with one of our customers a couple of weeks ago, and he told me he's really interested in this technology. They would like to do 1,000 calculations a day, and they don't have the internal GPU cluster, and ask for the suggestion. So I kind of tell him the AWS is probably the very good option. It's very secure. It's very scalable. And at Schrodinger, we are very well aware of the scalability of the AWS. On 2012, we have using 50,000 cores to do the virtual screening. And as mentioned in yesterday's keynote, we also using more than 50,000 cores to do to help one of our customers to design the solar cell with the help from cycle computing. Most importantly, it's very affordable. For each FEP calculation, it only costs about $4 on the G2 instance. And if the job doesn't need to be run right away, and if you look at the on-demand price on the G2 instance, it's very comparable to the internal Tesla cluster. So our internal utilization rate, it's about 70%. And if you're looking at the number of the G4 780 number, you might think that's probably the way to go. But don't get misled by that number. So you see the utilization rate there, it's 50%, because those cars, it's actually not very stable. It took us 2 months to get it up running, and the failure rate is about 20%. And we end up have to downclock some of those cards in order to make them run stable. So it's very clear AWS it's the way to go. So in the next couple of slides, I would like to share with you guys what AWS allow us to do. So this is the architecture of the product. So the current generation of the product, we only have a very minimum of support on the cloud. So users still have to transfer the file to the cloud and then run the job from the command line and copy it back. We are actively working on a new generation of the product, which is cloud-oriented. It's developed on the cloud and only deploy on the cloud. And as you see, security is very important to our customer. So we have the VPC over there, and also we have the VPN connection to the our client's corporate data center. And the only thing the end user will interact, it's the web server. Once they decide which molecule to run FEP calculation on, the application server gonna kick off the GPU cluster and run the job. When it's done, the result will be deposited back to the database and notify the end user. Since we generate a huge amount of data on the cloud, there's no way for us to download those data back to the local desktop to analyze or visualize. So the new capability of the G2, it actually will enable us to process those data and visualize it on the cloud. This is one of the retrospective study we are doing. We try to compare how good our prediction compare to the experiment. So the x-axis you see here, it's the experiment number, and the y-axis is the prediction. As you know, the experiment usually will have half-unit error. So in our prediction, 70% of them it's within the 1 unit. And the correlation, it's very high. It's almost 0.6. By the way, in total, there are 150 molecules, and this whole job could be done less than 2 days in our 200 GPU cluster. So when company X hear about the cutting edge technology we have, they reach out to us because some of the people in their organization and still have some skepticism about the technology. So they ask us to do a blind testing. They give us about 300 compounds, no experiment data in advance. And those compounds, it's already filtered by their best in-house technology. So the 9 out of the top 10 compound we pick, it's the very active compound. And the probability to achieve the result is good. It's less than 1%. And their scientists say even one active compound, the medicinal chemists will be really happy already. If they have this technology in their disposal, they will make only half of the compound. And the best compound we predict, it turned out to be the compound to help the project moving forward. And the chemists comment, if they have this technology at the time, they may save them years of the time already. So after the blind testing, the company X is really happy about the result, and they are signing a very big contract with us. And we are in the process of transfer the technology to them. There's another company, Y. They also really interested in the technology. Again, because there's some people still skeptical about the technology. They asked us to do another blind testing. It turns out 8 out of 10 active compounds we predict are the most active one. Again, the probability is very low. And when their head of the medicinal chemists hear about our prediction result, they reach out to us and ask us if we could provide a turnkey solution for several hundred GPUs. And this is actually a live project with a company, Zig. So the blue bar you see here, it's the time they use the best technology they have, no FEP. 1 out of 7, those compounds they propose are active. And the orange bar show you here, we made 8 total prediction. 4 out of the 8 are the most active compound. And the gray bar here, it's those compounds are the one the FEP predict. Those are not active at all, but they go ahead to make it because some of the chemistry, it's simple. Those all turns out to be really bad. And after this, company Zig have signed a contract with us and using this technology very aggressively in many of the projects they have right now. To summarize what I'm just talking about, I'm hoping at this point I could show you how useful the computer-aided drug design will help to drug discovery. And the new technology like FEP combining with the GPU computing will accelerate the drug discovery process, helping the pharmaceutical company to bring the drug to the market quicker and save more lives. And cloud, it's definitely a very viable solution for the high-performance computing, especially when the new G2 instance is online. And Amazon, it's definitely the leader right now on the GPU computing at the cloud. John, hand it back to you for the Q&A.